Okay, so let us next see initial value problems, boundary value problems and existence of solutions. The existence part we are going to see afterwards. Let us first see what initial value and boundary value problems are. And we are going to start with this example. This example has two things, a differential equation and another extra condition. We have already seen this differential equation before. But what about this extra condition? Let's see. So what we are requiring here is a solution to this differential equation that also satisfies this extra condition. That means it should be a function f which satisfies the differential equation and its value at the input 1 should be equal to 4. Now we have seen this equation in example 9 and there we stated something. We stated that these are all the solutions to the differential equation without proof. We are yet to prove this. We will prove it afterwards. For now, let's just assume that these are all the solutions. This is a one parameter family of solutions and that's all. These are all the solutions. So now what we are requiring is that we are seeking that member of this family which satisfies this condition. That means when x is 1, y needs to be equal to 4. That is, this is what we require. 4 should be equal to 1 square plus c. But then what happens to c? C has to be equal to 3. In other words, the member that we are seeking is y equals x square plus 3. Or if you want to write it as a function, I mean this is more like an equation, you can write f of x equals x square plus 3. So this is the particular solution, one member of the entire family of solutions, whereas this family is the general solution. Now the question is this: why did we suddenly consider an extra condition with a differential equation? That is because this is how differential equations generally arise in applications. In applications where they arise, you will rarely see just one differential equation. Almost always they come with these extra conditions. Here you have only one, there may be more such conditions. These are called supplementary conditions. And there is something about these conditions that will tell us what an initial value problem is and what a boundary value problem is. Okay, so that's what we are next going to see. How many values of the independent variable x do you see here in this? Here we have only one condition, so obviously there will be only one value of x. So the type of problems where that happens, where the supplementary conditions involve only one value of x, they are called initial value problems. But in general, this type of problems are called boundary value problems. All of them, including initial value problems. So an initial value problem is a type of boundary value problems where only one value of the independent variable x is involved. But if say two values are there, say f of 1 is 4 and the derivative of f at 2 is something else, then you have two values of the independent variable 1 and 2, then that will be called a 2-point boundary value problem. So in that sense, an initial value problem is a 1-point boundary value problem. So this is what the thing is. If the supplementary conditions involve only one value of x. X of course is the independent variable. Then the problem is an initial value problem, which we will write in short as IVP, or a one-point boundary value problem. Okay, a general boundary value problem will be called a BVP. As opposed to this, if say two values of x are present or involved, then it means the problem a two-point boundary value problem, which is not an initial value problem. We are going to see some examples after this which will make this classification more clear. Two-point BVP. Okay, like that 3-point BVP, 4-point BVP. In general, this type of problems where you have a differential equation with some supplementary conditions, they are called boundary value problems. Let us next see this example. In this example, the differential equation is this. It's a second order equation, linear, and you see two supplementary conditions. One of them is y of 1 equal to 3, and the other one is the derivative of y at 1 is equal to -4. Although you have two conditions, but only one value of the independent variable is there in them, which is 1. That is why this is an initial value problem. See, the number of supplementary conditions is not determining whether it's IVP or general BVP. The number of values of the independent variable involved is determining that. And we will see later that this has a unique solution. Okay, let us see another one. In this one, again the differential equation is same. See, this means that the problem in example 11 is also an initial value problem. There, however, there was only one supplementary condition. The differential equation is same. However, here two values of the independent variable x are involved and they are present in the supplementary conditions, 0 and pi over 2. So this is not an IVP, this is a 2-point BVP. This also we will see later has a unique solution. And if you go back and see example 11, there also you see what we found there, y equals x square plus c was the entire family of solutions, and among them only that one solution satisfies the extra supplementary condition, which is y equals x square plus 3. Okay, that at 1 its value is 4. So that solution is also unique. So is it in general the case that whenever we consider a boundary value problem, which may be an initial value problem or 2-point or higher point boundary value problem, are we always going to have unique solution? No. This next example shows that this is not the case always. But if you consider this other problem, again the differential equation is same, but the supplementary conditions are different. Y of 0 is 1 and y of pi is say 5. So these are our supplementary requirements. This boundary value problem, 2-point boundary value problem, has no solution. Okay, so that type of things are also, that is also possible. This also we will see later why it has no solution. You see, you have to understand that the original differential equation may have solutions, but when it comes to satisfying the extra boundary conditions or supplementary conditions, there you may have problems. So this one has no solution, and this tells us that we should investigate which differential equations have solutions and which do not have solutions, and that is why we have that thing also, existence of solutions in this discussion. Now let us first define some things. Okay, let us look at this definition. Consider the differential equation, first order differential equation, which we considered before also when discussing the geometric significance of such equations. Let us give it some name or number. So let me call it star. Okay, where we are now going to put some restriction on the function f. F is a function from d into r, and this is continuous on d. And what is d? D is a subset of R2, naturally, because the input is a vector with 2 components. So obviously the domain has to have that type of elements, so it has to come from R2, and not just any subset, is a domain, okay, which if you remember is an open connected subset. Topologically it is open and connected with R2 with its usual topology, which comes from the Euclidean metric. Okay, so this is what we have said now, and we are going to consider another thing. We have the differential equation, and now we will consider a supplementary condition. Let us choose any point x naught comma y naught within that domain D. Then right from here, then the initial value problem IVP associated with the present equation, that is associated with this equation star and this point, is about finding a function, some function phi from I to R, where I is an interval in R with x naught in I. Okay, with the point x naught, the real number x naught in I, such that this phi is a solution of the differential equation star and phi of x naught is equal to y naught. So this is that supplementary condition which the function phi has to satisfy. Okay, so if a differential equation like this is given to you, and remember this f is continuous on a domain, it is defined there also and it is continuous, and you have chosen a point D, then the initial value problem associated with all these ingredients is it's about finding a solution like this phi which also satisfies this supplementary condition. Why do we need continuity here? That it's coming soon. But before that, let us also discuss about how to find this phi. See, we have still not said anything about whether a phi will exist or not. That existence part we are still suspending, okay, for now. But the question is this: say a phi exists in the present situation, how to find one such phi? That of course depends entirely on the function f itself, or rather its form. For some special types of f, there are definite methods that will let you solve this differential equation. If you follow those methods, then you can solve the differential equation exactly. Exact solutions are available for some equations with special types of forms that f may have. And then what you do, say you have solved one such equation and you have found a one parameter family like this, okay, which is some relation involving x and y and that parameter c. Then what do you do to find that member of the family which satisfies this? Well, that's easy. In that relation, you substitute x naught for x and y naught for y, and then you are getting an equation which has numbers and c. You can then solve for c. Whatever value of c that you get, say if we call it c naught, you then use that value back in the general equation of the family, and this will be your particular solution, or that, well, not exactly, not technically that phi, but this will be a relation from which phi can be found as an explicit solution, because this may be a particular implicit solution, right? For example, you may get it in the form x square plus y square equal to c naught. From that, you then will have to solve for y in terms of x. So, that may give you some explicit solution. And in fact, this is what we did in this example 11, right? All right. Now, the geometric interpretation of this entire thing is, of course, the geometric interpretation of an initial value problem is that what do you get geometrically when you solve such an equation? You get integral curves. You get a one parameter family of solutions. So, the individual members of the family are the integral curves, that is the graphs of the solutions. So, you have to find that integral curve from the family which passes through this point. That is the geometric interpretation of an initial value problem and its solution. So, let us now illustrate this in this next example. Say now our IVP is this: dy dx equals minus x divided by y, and the supplementary condition is y of 3 equal to 4, and you have to say solve this. To solve this, of course, you should know a family of solutions for the differential equation first. Say you know that this is a one parameter family of solutions. Actually, you can verify. It's a different matter that if you ask how one can come up with such a family, because unless you have this, then how can you verify whether this satisfies the differential equation? We are going to see those things later. Okay. For now, let us assume that this is the one parameter family of solutions. So, then what do? Obviously, you have to find that value of c for which this is true. That means c square should be equal to 3 square plus 4 square, which is 25. So, this relation in this case is x square plus y square equal to 25, and from this relation now you have to find y as a function of x. If you just blindly solve for y, this is what you will get. Minus x square. However, you need to decide in which interval. It has to make sense also, no? For whatever x values you are going to calculate this function, you should get a real number again. Well, you have square root, so the expression under the radical sign needs to be non-negative, greater than or equal to 0, and that happens in this interval, in the closed interval minus 5, 5, because if your x is coming from there, then its absolute value is less than or equal to 5, and so its square is less than or equal to 25. So, 25 minus x square will be non-negative. So, on this interval you can define this function, but there is a problem. Say, for the sake of being specific, I take only the positive one. Now, it has to satisfy the differential equation also, right? And for that, it should first of all be differentiable. So, if you apply your calculus formula again blindly, using chain rule and everything, this is what you get, 25 minus x square, and then you just cancel it 2. Yes, so you seem to be getting really the differential equation because this is your y, so you can put y here, but there is a problem. The problem is that the derivative does not exist at minus 5 and 5. Well, I mean, does not exist means it becomes infinite. Okay, you can see geometrically why that happens. This is just going to be the half circle, right? Semicircle. This is 5 on this side it's minus 5. So you know how a semicircle meets the a semicircle like this meets the x-axis vertically. That is why if you think of the derivative of this function at 5, say, you are thinking about the slope of this line. Alright, so that is infinite because the line is vertical. The same happens here as well. That is why you have to remove these boundary points from the domain. And so this is the interval on which you can define these functions. But which of them should we choose? We need, of course, y of 3 to be equal to 4. So we do not need negative, we need positive. And that is why this is our solution, particular solution. If we write it as a function, then this is what it is, 25 minus x square, where x lies in the open interval minus 5 comma 5. Okay, so that's how we can find one particular solution, which is also the only solution of this initial value problem, not just the differential equation. The differential equation along with that supplementary condition. Alright, now next comes the question of existence. Now we go to the existence part. So this is B. Existence of solutions. So we have already mentioned that this boundary value problem has no solution. Y of 0 is 1 and y of pi is 5. It's a second order equation, 2-point boundary value problem. At least we can say something about whether a solution exists for the problem that we defined just now in that definition. An initial value problem which involves a first order differential equation. That means our star, that initial value problem. Okay, for that problem there exists always at least one solution. So it's a different matter, you may not be able to find the solution exactly for some f. The only condition is that f needs to be continuous, which was the condition there. And x naught comma y naught of course has to come from the domain D of f. You are assured that there is one solution. The theory tells us that that should be the case. But then next comes the question of whether there can be more than one solution, the question of uniqueness, because wherever there is existence there will always be uniqueness of anything. If something exists, naturally the next question you ask is whether that is the only thing of its type. Let us next see this example where more than one solution is present. Let's consider this initial value problem. dy dx equal to the cube root of y and the supplementary condition is y of 0 equal to 0. Let us first consider this function f1 from r to r, which is nothing but the constant function 0. Oh, and by the way, is it really that type of IVP which we considered in that definition? Is this a continuous function of two variables? Yes, it is. I am not going into the details of how this is continuous. You recall your things from real analysis, which tells you that yes, this function is continuous, and not just that, it is continuous on the entire plane R2. The problem that you usually have with square roots and negative numbers is not present here with cube roots. And one more thing, do not forget that this actually has to be interpreted as a function of two variables x and y, although x is not present here. That's a different matter. Okay, so we are assuming that this is continuous. We know that this is continuous. Fine. So there exists at least one solution, but now we are going to see more than one solution. One of them is this. Why? Well, is the constant function differentiable? Yes, it is differentiable. And what is its derivative? That is also the constant function 0. So that means the left hand side is constantly 0. What about the right hand side? The cube root of 0 is again 0 at any real number, which may sound a little confusing. I mean, if you take the cube root of the constant function, then at every point that will be equal to 0. In other words, that's just the constant function 0. And is this supplementary condition also satisfied? Yes, of course. Everywhere it's 0, so obviously at 0 also it's 0. That means this is one solution. Now we are going to see another one, a different one. This f2, however, has been defined partly in parts, and the definition is this: 2/3 times x to the power 3/2. No, I think it's on the entire. Okay, so both of these things. If x is non-negative and 0 if x is negative. Let us verify that this is also a solution. Since the function is a little complicated, so the verification will, you have to put a little effort into it. Let us first see the easy thing. Is this condition true for this function? When x is 0, you have to use this part of the definition. So then 2/3 times x is also 0, and that to the power 3/2 is also 0. Yes. Next comes the question of satisfying the differential equation. For that we need to know, oh, I forgot to write x, the derivative of f2. If x is greater than 0, then you can find the derivative of f2 at x by using your usual calculus formula, chain rule and those things. And it will be 3 divided by 2 times 2 divided by 3 times x to the power 3 over 2 minus 1. So you are first differentiating with respect to 2 over 3 times x, this power, and then according to chain rule you then have to differentiate this inside with respect to x. So that will give you 2 over 3. So you are ultimately getting what? 3 over 2 minus 1 is 1 over 2. So at a positive real number, this is the derivative. What about at a negative real number? That's even easier. If x is less than 0, at a negative real number and around that number in a sufficiently small neighborhood, it's the constant function 0, like this one. And that's why the derivative is also 0. However, what happens exactly at 0? For that we need to calculate the left hand derivative and right hand derivative separately, because the function has been defined separately on two sides of 0. Let us first see the left hand derivative at 0. So it will be what? By definition, limit left hand derivative. Okay. So h has to approach 0 from the left side, and f2 of 0 plus h minus f2 of 0 divided by h. There is a reason for choosing the left hand derivative first. 0 plus h of course will be h. Because h is approaching 0 from the left side, actually h is negative. So for negative h, what is f2? By definition that is 0. And what is f2 at 0? That is also equal to 0. 0 minus 0 divided by h, that has the limit 0. Okay, so left hand derivative is 0. Next we see the right hand derivative. Right hand derivative similarly is this limit. This time if h is approaching 0 from the right side, f2 of 0 plus h minus f2 of 0 divided by h. Now however we have to use this part of the definition because h is positive now. f2 of 0 is 0, so this is what we will get, 2 divided by 3 h to the power 3 divided by 2 divided by h. Okay. Yeah, the function definition of course we know, we can recall. So let me wipe this place off. So you can of course take 2 over 3 to the power 3 over 2 outside. And h to the power 3 over 2 minus 1 means h to the power 1 over 2, which is just square root of h. And this limit you already know is 0. So this is equal to 0. So yes, the function is in fact differentiable at 0 also, and the derivative at 0 is equal to 0. That is, now based on all of this, we can write the derivative also as a partly defined function. How? Well, what do you see here? Let me write it here in this part. What is f2 prime at x when x is positive? This is the derivative. 2 divided by 3 times x to the power 1 divided by 2. when x is positive. When x is 0 and when x is negative, the derivatives are equal to 0. However, if you put x equal to 0 here, then also you get 0. So, you can slightly change the definition and club 0 with that upper part. So, this is what the derivative of f2 is. Okay. Now, what was the original f2? Let us again write its definition. The original f2 was this: 2 over 3 times x to the power 3 over 2 when x is non-negative and 0 when x is negative. Is the derivative equal to the cube root of f2? Let us take the cube root of this function. What will happen when x is non-negative? You have to take the cube root of this. And by rules of exponents, that 3 and cube root will cancel each other and you will have this. And cube root of 0 is 0. You see, same. That means f2 prime of x is really equal to this. So, yes, this is another solution of that same initial value problem. Why is this different from the constant 0 solution? Well, because it is not constant. For example, you can take x equal to 1. At that point, what is the value of this? Well, not this, but this one. What is the value of the function? It is 2 over 3 to the power 3 over 2. Whatever real number that is not equal to 0. So, f1 and f2 are two different solutions. So, we do not necessarily have uniqueness, but we can have uniqueness and existence both if we put one extra condition more, besides having f continuous, another extra condition. So, this next theorem is about just that. You may be wondering where is the proof for that one, which states that there is at least one solution. We are going to see the proofs and the theory part afterwards. Okay, well, first of all, we have to learn the methods for solving the equations, and then we can go to the deeper parts where we ask why a solution exists. So, this is theorem 1.1. This is basic existence and uniqueness theorem. Okay, so the theorem of course is this. Consider the differential equation dy dx equals f of x comma y. Do you see how many things you have to consider just for a first order equation? We haven't even got to second order equation. Okay, so this is how things are, where f from D to R is a function and this is the domain. Okay, so basically we are just repeating whatever we did in that definition, but extra things are going to come. Let this be a point in D. Okay, now the conditions. Let means assume f and the partial derivative of f with respect to y be both continuous in D on D same meaning. That means at every point of D f is continuous. F is already defined on D. Okay, so the question of it being defined on D is not there. It's defined on D, that means it has a value at every point, but it also needs to be continuous at every point. And the partial derivative of f with respect to y, not with respect to x, okay, with respect to y, needs to also be defined on the entire domain D, and itself should also be continuous as a function on D. If these two things are true, then for some real number h which is positive, sufficiently small, there exists a unique, this time we have uniqueness, a unique solution phi. Well, are we calling it phi? Actually it does not matter, we can call it anything, but I just want to be consistent with the book. Okay, so then there exists a unique solution which is a function of this type, which has that point x naught as its midpoint, I mean its domain, and is this closed interval of the differential equation such that it also satisfies the supplementary condition. If it's an initial value problem, the supplementary conditions are also called initial conditions. Okay, so this is a theorem that we are going to use. Its proof you won't see now, you can probably guess. We are now at this moment not presenting proofs. The author is not presenting proofs now itself. In chapter 10 we are going to prove this with less restrictive hypothesis. The hypothesis will be weakened a little bit, and then in that case we are going to prove it. So we are still far away from proof. Instead, let us see how one can use this to say something about initial value problems in these next two examples. And with these two examples, this section actually ends. The IVP we now have is this: dy dx equals x square plus y square, and the supplementary condition is say y of 1 equal to 3. Okay, let us now apply this theorem to this IVP. First of all, we need to consider, I mean that's the only thing we have to see. We have this function f of x comma y equals x square plus y square. That D in that statement in this case is R2. Is R2 a domain? Is it open? Yes. It's the entire metric space, it is open. Is it connected? Yes, it is also connected. And is F continuous? Yes, F is continuous. To prove continuity of F, either you use the several results that you have about continuous functions between Euclidean spaces, or you just directly note that this is a polynomial function in x and y and such functions are continuous. It is a fact, okay, it is the result in fact in itself. So, this is a continuous function and that too at every point of R2. Next we have to see the partial derivative. Partial derivative with respect to y is of course 2y, which itself is also a polynomial in x and y. X is not present there, that is not a problem. So, this is also continuous throughout R2. So, yes, our theorem is applicable here, and the theorem tells us that this IVP has a unique solution which is going to look like this. See, you have to understand that the theorem is an existence and uniqueness theorem. It says that a unique solution exists, but it won't tell you how to find the solution. You may have the impression initially that then it's just useless. No, it's not useless. It is telling you that a solution exists, so now you can go looking for that solution. If somehow the solution does not exist and you can know beforehand, then that's it, that's the end of story. There is no need to spend any more time on that IVP. In fact, this is what we also said in our previous discussion, that from the theory you will know that a solution exists, so you can spend time, energy to find it. What is the purpose of knowing that there is only one solution? Well, that is also clear. If somehow you really find a solution, you can be sure that okay, my journey is over, there is no more. Okay, that's why if you have uniqueness and you found one solution, that is the solution. That's where the importance of this theorem lies. And finally, let's see this. Here actually there are two IVPs. The first one is this. This is y divided by root x. Yeah, now this looks a little problematic. Y divided by square root of x. And the initial or supplementary condition is that. What about this one? Let us first draw a diagram. Okay. We need to see what type of function this function is as a function of x and y. So, this is our plane R2. And we now need to first of all look at the point 1, 2. So, I just considered the point 1, or let me show it a little away from the axis. So, this is my point 1, 2. What type of problem does this function offer? offer, I said cause. Okay, see, the problem here is that it is not defined for all x and y. Not only do you need x to be non-zero because it's appearing in the denominator, but you also need x to be positive because it's under square root. So x needs to be positive. Y, however, can be anything. What does that mean? It means that whatever domain you choose for this function, that has to lie on the right side of the y-axis and also without touching the y-axis. Many possibilities are there. You can just choose an irregular region like this, okay, which contains the point 1, 2 because that's the condition, otherwise it won't make sense. So you can see, I mean, in this figure itself, that this is a connected set, connected subset in R2. You just assume that the boundary is not a part of the set, like what you have in open balls. So this is that type of set, then it will be a domain. On this type of set, you can consider this function. Okay, so then there is no problem of it being undefined at some point, because you are avoiding the y-axis, and on the points on y-axis, in them x coordinate is 0. Alright. So what? Let us also see that on such a domain D, this is a continuous function. Again, I am not going to say how, you decide from your knowledge of analysis or calculus. What about this partial derivative? If I am calling this say f is continuous and f is defined on D. The partial derivative with respect to y is this. This also exists at every point of D and is continuous. The author actually has chosen a more regular shape, I think something a square like this, whose midpoint is this 1, 2, anything you can choose as your D. So by theorem 1, this IVP also has a unique solution. However, let us next see this second one, where the differential equation is same, but the initial condition is a little problematic. The initial condition or supplementary condition is this: y of 0 equal to 2. So let us first see where the point is lying. Zero comma 2. It is here somewhere. Now here's the problem. What do you want? If you really are, you want to use theorem 1, you need this function to be defined in a domain that should contain this point, and the domain needs to be like this. Now note that no matter how hard you try, you can choose D as small as you want, you can change its shape, its orientation, whatever, you can change many things, but you cannot avoid these points which lie on the y-axis, and they will also lie inside D. They will make this function undefined, because at these points the x coordinates will all be equal to 0. Note one more thing, that you cannot get away by choosing a D like this. No, D is open. So for this point 0 comma 2 to be a point in D, it should be an interior point. Okay, so it cannot lie on the boundary of D. So that prevents you from choosing a D like this. What does that mean? It means, you see, there is no point looking at the partial derivative. The function itself, it cannot be defined on any such D in which it is continuous. Cannot even be defined, forget about continuity. So, theorem 1.1 is not applicable here. Applicable to this IVP. Does it mean that it does not have a solution or it does not have a unique solution? We don't know. Okay, we don't really know, because we cannot apply this theorem means the theorem does not give you any information about this IVP. It may have solution, who knows, but this is not the tool for knowing that. Okay, and with this section ends. After this we have exercises that of course we will solve in the next differential equation video. And what do we have tomorrow? I forgot, so I won't say anything. Okay, whatever it is we will see tomorrow. So that's just it for tonight, or should I say day. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.